The sum of the perimeters of a square and an equilateral triangle is 10. Find the dimensions of the square and the triangle that produce a minimum total area. All right, so let's see what we're working with here. We have a square. Okay, with a square, each side has the same length, so each side, we can call that x. And then we have an equilateral triangle, which means all three sides and all three angles are equal. So we'll call this y, y, and y. And the sum of the perimeters of a square and equilateral triangle is 10. So what does that tell us? That tells us that the perimeter of the square, which is 4x, plus the perimeter of the equilateral triangle, which is 3y, the sum of these is equal to 10. Now we want to find the dimensions of the square and the equilateral triangle that produce a minimum total area. Okay, so we need an equation for area. So the total area is the area of the square plus the area of the triangle. So area of the square is x squared. Okay, we know that. Plus the area of the triangle, which is 1/2 times the base times the height. Which means, what is the height? What is the height of this triangle? Well, let's cut that triangle in half and look at half of the triangle. And if we do that, this angle is 60. This angle is 90, which means this angle has to be 30. So we have a 30, 60, 90 right triangle. And we know the hypotenuse is y. The base of this is half of the base of the equilateral triangle, so that's y over 2. And if the short side, the side opposite the 30, is y over 2, then the side opposite the 60-degree angle is the short side times the square root of 3. So that should be y root 3 over 2. All right, so that's the height of that equilateral triangle. All right, so 1/2 times the base times the height, y root 3 over 2. Now let's clean this up a little bit. And so we have area is equal to x squared plus y squared times the square root of 3 over 4. So that's what we get here. All right, so this is our primary equation. Now, if we're trying to minimize something, and sort of minimize the area, we're going to have to take the derivative. But the problem is we have 3 variables here, a, x, and y. So we can't take the derivative yet. We have to get rid of one of those variables. All right, so what we're going to do is come back up here to this equation, this relationship between x and y. So if we want to get rid of the x in our primary equation, let's solve this perimeter formula for x. So if we solve for x, we get x is equal to 10 minus 3y, and then we have to divide that by 4. All right, so what we're going to do is take this expression that tells us what x is equal to and plug it in for x. All right, so a is equal to x squared. So we have to square the x, so that's 10 minus 3y squared. And we could square the 4 on the bottom, that's a 16. And then we have y squared times the square root of 3, all divided by 4. All right, so this is our secondary equation. Primary equation. Our secondary equation is what we get when we take our equation for area and eliminate one of the independent variables. So now we have an equation with just a and y. A is dependent on y, so we could take the derivative here. Now if we want to find the minimum could only happen at critical values. So the critical value is where the derivative is equal to 0 or undefined. So we're going to have to take the derivative. So dA dy, derivative of a with respect to y, because y is the only variable left. All right, so first term, we can apply the chain rule. The 2 comes out front, inside stays the same, power drops by 1, times the derivative of the inside, which is a -3. And we have a 16 on the bottom. And now, with that second term, well, √3/4 is a constant, so we're just taking the derivative of y squared. So that's 2y times the square root of 3, and that's still divided by 4. Okay, now let's clean this up a little bit. The 2 and the 4 cancel to a 1 and a 2. The 2 and the 16 cancel to a 1 and an 8. So if we clean this up, it looks like we have a y times the square root of 3 divided by 2. That term's positive. This term's going to be negative. And so we're subtracting off a 30 minus 9y. And that is divided by 8. All right, so this is our derivative. This is our derivative here. Derivative of a. All right, so when is the derivative equal to 0? That's where our critical values are. Those are the potential places where we could have a minimum value. So we'll take this and we'll set this equal to 0. All right, so let's solve that equation. We could multiply both sides of the equation by 8 to get rid of those denominators. So we'll have a 4 times the, don't forget the y, 4 times y times the square root of 3. And then a minus, and we'll distribute the minus sign, so that's a minus 30, and a minus 9y, so that's a plus 9y equal to 0. And so let's move the 30 to the other side, add 30 to both sides, and we could factor out that y. So on the left, we'll have y times 4√3 plus 9, and that's equal to 30. And to solve for y, we could divide both sides by this 4√3 plus 9. So we'll have y equals 30 divided by 4√3 plus 9. So we have one critical value for this function. So now we have to make sure this critical value is a minimum. So I'm going to actually apply the second derivative test, because taking the derivative of the derivative, or taking the second derivative, is pretty easy in this case, because all we're going to use is the constant multiple rule. So we have the derivative. So let's switch to red for the derivative. The second derivative of a with respect to y is equal to, well, the derivative of √3/2 times y, that's y to the first power, so that's just √3/2. And then we have the derivative of -30/8, that's a constant, so the derivative of that is 0. And the derivative of -9/8 times y is negative 9 over 8. And so we have a minus minus, so that's plus 9 over 8. So the second derivative is constant. And the second derivative is positive. So the function for a is always concave up. Second derivative is always concave up. And if the first derivative is equal to 0 and the second derivative is positive, the second derivative test, which we covered in a previous video, the second derivative test tells us that's a minimum. Okay, so that tells us we have a minimum here. Minimum when y is equal to 30 over 4 root 3 plus 9. All right, so that works. There's our minimum. The area is minimized when y is equal to 30 over 4 root 3 plus 9. But we also need the dimensions of the square. So what we're going to do here is we're going to look back at this guy. That's our equation for x. So x is equal to 10 minus 3y over 4. X equals to 10 minus 3y over 4. And we already know what y is. Y is 30 over 4 root 3 plus 9. So that's 10 minus 3 times 30 over 4 root 3 plus 9. And that is all divided by 4. So we have to do a little simplifying here. Let's see. We've got a 10 minus, we could distribute the 3, so 90 over 4 root 3 plus 9. And that's all divided by 4. Let's get a common denominator on top. So that's 10 times the 4 root 3 plus 9. So that's 40 root 3 plus 90. And then there's a minus 90. And that's all divided by 4 root 3 plus 9, and we still have that over 4. Right, so we have this is nice, we have a plus 90 and a minus 90. So it looks like we're down to 40 root 3 over 4 root 3 plus 9, and we're dividing by 4, so let's multiply by 1 over 4. And the 40 and the 4 cancel, so it looks like we're down to 10 times the square root of 3 divided by 4 root 3 plus 9. And that's our value for x. All right, so looks like we're good. We solved for y. Y is equal to 30 over 4 root 3 plus 9. That's the length of each side of the equilateral triangle. And we solve for x. That's 10 root 3 over 4 root 3 plus 9. That is the length of each side of the square. And if we have this value of x and this value of y, and the perimeters add up to 10, if we use these dimensions, this minimizes the total area. And we could have used the first derivative test as well to verify that we had a minimum, but I think in this case the second derivative test was easy and pretty straightforward to use. All right, so looks good. We started off by interpreting the problem. It always helps to draw a diagram. We came up with our equation for area, our primary equation, And we eliminated one of the variables to come up with our secondary equation. So there was only one independent variable, and then the minimums could only occur at critical values. So we took the derivative, set the derivative equal to 0, solved, found a critical value, and then used the second derivative test to verify that a minimum did occur at that critical value. And once we had that value for y, we went back to our relationship between x and y and solved for x. All right, that does it for this one. I hope it helped.